our anomalous SAR image detection. The company that we work with is Asterra. My partners are Sarit and Talex. I'm Eran. Talel's our mentor for my data. Inon Sharoni, AI lead from Asterra. Now we'll watch a short video about Asterra.
What started as a search for water on Mars, on Earth became Asterra. Experts in underground soil moisture and leak detection, we are now saving the world billions of gallons of drinking water annually. And that's just a glimpse of the potential of our technology and our vision for the future, to be better citizens of a more sustainable world. To make that possible, Asterra has grown beyond leak detection to provide infrastructure data across industries. Soil moisture for road, rail, and mining, and for earthen dams and levees. Pipe condition assessment for water and wastewater. Ground conditions for infrastructure planning. Unprecedented infrastructure intelligence driving more informed decisions to build the future we envision. A safe, clean, efficient, and sustainable planet for all. Asterra, the intelligence to what started as a search.
Okay, cool. So now after we learn about Asterra mission, let's learn about Asterra's pipeline. So everything starts with the SAR satellite. The SAR satellite sends the radio waves to the underground. The radio waves collects data and then return back to the satellite and eventually generates a SAR image. The SAR image is an input to the machine learning model. The machine learning model predicts whether there is a leak or not under the ground. And in case that there is a leak, the field team is sent to this place to take care of it. So shortly we can say that we can see unseen from space underground. Yeah. So our project is before the main the prime machine learning model. Our project is to detect and identify anomalous SAR image detection. And the question is, what is anomalous, what is normal, and we'll answer it shortly. And here we can see a very simple examples of anomalous SAR images, such as the green stripes, incomplete image, the red dot, etc. And now each of us will tell about his own journey with Asterra and how it combines together as a model.
So guys, we're open source project, as you understood already, and we're Team Sarat. This is our shorts as well. So basically, to be open source, it's to serve on multiple targets. So that was our data choice as well. So we're not only taking the Asterra data, we also getting 2.5 million roughly SAR images all over the globe, including Google Earth Engine. We need to stress that in the open source data, we didn't have labels. In the Asterra data set, we can get the indicators. So right now you can see the examples of the data variety. It's a grayscale, it's the colored image, it's the urban, it's the bare land, it's a agricultural land. So the challenge basically right away comes if you're training the model on the agricultural samples when you put the bare land one image in the validation set, it gives you the anomaly. It's not.
Okay, so now let's see if we can spot an anomaly together. So here on the right, you can see an example from the public dataset. We've mentioned we had 2 polarization channels in the public dataset, and it was unlabeled. Here is an original SAR patch, and next to it, you can see a SAR patch where we injected some salt and pepper noise, and this is how we created the synthetic anomaly. So we also mentioned that we had Asterra dataset. So any one of you can guess which of them is anomaly and which of them is normal? this one is the normal star image, and next to it is the anomaly star.
So basically, salt and paper was not enough for us to be represented our anomalies. So we decided to make it more interesting and sophisticated for the models. So we introduced the stripes, inversion, like different size of squares everywhere in order to validate how our model actually do.
Okay, so now that we've talked about the data, let's talk about the system design of our pipeline. So the first layer is the data preprocessing, where the input is a star image, and we are applying different preprocessing steps like normalization and patch extraction. Next stage is layer 2, where we introduce you a 4-model path. We use different models in order to detect the anomaly. First model is RX algorithm, which is a statistical-based algorithm that identifies anomalies in SAR images. We also had an unsupervised approach where we use variational autoencoder, supervised approach using Siamese network, and transfer learning with Dino version 2, which is a vision transformer developed by Facebook. And the last layer is the post-processing and final decision, where we are taking the anomaly scores from all the models, and we aggregate them for a final decision, and we alert whether the input image is anomaly or not.
So, okay, here we go. Let's dive deep in our RX algorithm, which is statistic-based. So what we did, we took image, we did patching. Based on RX score, we can easily label the extreme anomalies. So basically what algorithm does, it's like measures the miscellaneous distance between pixels. And if RX score is roughly high, we can like label it like anomaly. Right? Easy breezy, right? Wrong. So we have the one anomaly which is extremely high, like one of many anomalies, but this is the example like we're giving you, which is almost 35, threshold is 11. Here, the second anomaly, which is more sophisticated, is not giving us the high score. Actually, what it does, what it gives us in this algorithm, the next slide, it gives us the score lower than the very normal agricultural field. So basically, that's why we decided to go to the deep learning models further. So we need something that know better than learns better than right discharge and the extreme anomalies. So unsupervised latent space variational autoencoder. Basically, what we're doing, we're giving the patch, we're encoding the patch. In the latent space, the machine is learning how to decode this image. And based on the decoder, we have an estimation error of reconstruction. So here we go. We was very curious about, okay, how does this work? And actually, we introduce you with the what happens in the machine while it encodes and decodes images. It was like 6 layer steps, but we did it for one epoch for you to like have roughly the vision of what machine does. So basically, we have normal images and the normal scores, and this reconstruction score errors, because nothing is really very good enough, we're using to make a normal distribution window. So for us to say this image is good, and basically what we're doing, that if the other image comes and it's not fit into the normal distribution from any end, we can strongly suggest that this is an anomaly. And we can see it here. So this is our low order anomaly. You see, after 120 epoch, which is roughly what, model is pretty much reconstructed everything except the pattern, which we give her. And basically on these hash maps later, we can also run some regressions and pattern recognitions, etc. We can sophisticate it further. On the upper end, you have the model is struggling to reproduce the stripes. So we're also discarding it.
Okay, so now we'll talk about the Siamese network. So the idea here was to learn an embedding space where similar patches of normal and normal pair are close together, and these similar patches of anomaly and normal are far apart. So for this, we have patch A and patch B that went already the pre-processing stages and are now a fixed site. We took those patches and move it forward in sister network 1 and sister network 2, which are identical networks, and we create embedding. We also use contrastive loss in order to learn this embedding that we discussed about. And for this specific example where patch A is normal and patch B is anomaly, we are learning embeddings that are far apart. So now let's discuss the inference process. So in the inference process, we have a test patch that already went through the pre-processing stages. We transfer it to the Siamese network, the trained Siamese network, in order to create the embedding. And we also pre-computed embedding database that contains normal and anomaly samples. And we measure the distance between the test embedding to each of the embedding database. And using KNN, we find the 5 nearest neighbor and use majority vote to decide whether the test patch is anomaly or not. So the performance, we tested the model on 2,400 test patches, where 20% were anomaly and 80% were normal, which is high recall of 90%, meaning we identify most of the anomalies, but the precision here is low, meaning we also identify normal patches as anomalies. I do mention that Asterra wanted to give more weight to the recall because processing an anomaly can be very costly. You can see here also the arrow seeker where Asterra can choose the optimal threshold for them.
So in order to take it one step further, in order to understand what anomalous means on a Asterra side, sometimes anomalous cannot be seen for the human eye. So I decided to investigate it deeply, and based on that, to choose the fit model to our machine learning. So on the left image, we can see a T-SNE model, which based on a Dino B2. The T-SNE model categorizes the images into different clusters. We can see that the main cluster is a bright highlight, which means white pixels in the middle of the image. We can see a dark shadow, like we can see, like we can see in the middle of the image there, incomplete images and so on. And in the right, we can see a guard cam in the right image, and on the top left, we can see cut edges. And the stronger the anomalous, we can see more yellow, the stronger the yellow color. So based on these conclusions, where we have anomalous that not in specific area, can be in different areas inside the image, I decided to go with Dino. Dino is a Meta, belongs to Meta, and it feature extractor, which means that it extracts all the main feature of the image. It can find a small anomalies inside the image. It's a visual transformer and a self-learner, and the most important, it doesn't need GT or labels to work with. And now we can see the backbone of Dino V3, which was published 5 days ago, by the way. And the input is an image, as we can see on the left. Now we have 2 versions of the image. We have the close-up and the wide view, and we have the wide view for the teacher, and we have the both for the student. The student tries to learn from the close-up to the wide view by recognizes small patterns, edges, gable blobs, etc. And each time it tries to emulate the teacher image. Eventually, it generates a feature vector with all the important feature of the image. Next slide, please. Now let's go to the head. So the head gets the feature vector that we saw just earlier. The next step is attention pooling. It recognizes the most important part of the image, and it generates anomaly score by weights, which I think we can see in the formula below. And the next step, it compares to the threshold that we chose at the beginning. If the anomaly score above the threshold, it classifies as anomaly or not. And now we can see the model results. So the precision is 63%, F1 71, ROC 94%. I didn't mention before, but at the beginning we got a list of images of 127 images which suspected as anomalous, and we worked with there. Now I believe that with additional fine-tuning and maybe additional anomalous images, we can get to better results.
Okay, so we are about the future steps. Let's talk about the future steps. So we are not only data scientists, we are all presenting you the market-driven solution. So in the future, we see aggregation like a Sarat agent, which can grab output from all models, and we can operate based on the wages scale. He will take the decision if the image is good or bad.
And now we'll see a quick video from Asterra.
שלום לכולם, שמי ינון שרוני, אני מוביל את צוות ה-AI באסטרה. במהלך 5 החודשים האחרונים היה לי העונג לעבוד עם שרית, טליקס וערן. המטרות של אסטרה בפרויקט הזה היו לשפר את הביצועים של מודל הזיהוי שלנו, על ידי כך שאנחנו נזהה את התמונות שעלולות להיות בעייתיות באופן אוטומטי. צריך לומר שהפרויקט הצליח וגם התעלה על המטרות שלו. הצוות הצליח לא רק לזהות תמונות שהן חריגות, אלא גם לקבץ אותן לקבוצות של חריגויות דומות. הצלחנו גם להתייחס למקרים ספציפיים של כשלים, סוגי כשלים מסוימים של המודל שלנו בפרודקשן. ביצוע הפרויקט בשני שלבים, שהשלב הראשון התבסס על, בעצם יהיה קוד פתוח, התבסס על גם דאטה שזמין בעולם הפתוח, ובסופו של דבר גם יהיה גם חלק שני שיתאמן על דאטה מסחרי של אסטרה, שהוא דאטה פרטי שלנו, והצלחנו לייצר ככה גם איזשהו מוצר אופן סורסי שהצוות יכול להמשיך לפתח אותו ולהציג אותו. אני מאוד רוצה להודות לכרמל, פיני וטל מוואי דאטה, ובמיוחד אני רוצה להודות לשרית, טליקס וערן על ההזדמנות לעבוד איתכם. תודה רבה לכולם.
So basically in this point, we just want you to open your phones, scan our open source project, and start contributing. Maybe, I know, maybe you don't have time for that. We're also open for donations. And basically, you also can open a feature request for us. By the way, we are giving out 2 more t-shirts. So the first one who is doing the pull request here will get another t-shirt.
Yeah.
Thank you so much for being with us. Questions?
In general about the data, what was the regular rate of anomalies in the data that you got from Asterra? And just to understand, how much is it? Because you said that you created a data set of 80/20.
Yeah.
But what is the true expected rate of anomaly in the data? And another question is the data a sequence of images, or is it like standalone images. If it's a sequence, was there any value to using the previous or the next image compared to the one that's currently?
Yeah. Yeah. So we got from Asterra a list of CSV, which contains 127 images, and each image has a different confidence score regarding the anomalous. And from there, we needed to investigate the data because the company wasn't sure about the anomalous as well. It's something that we don't have duty to work with in the first place. So therefore, I used a Dino V2 because it doesn't need any labels to work with, and very helpful this case. Alex, do you want to add anything?
Yeah. So basically, to follow up on your question, it's very important to know your role, research of interest, right? Point of interest, because the pictures is huge. So that's why we got like approach. Okay, we will patch it to understand basically and to go dive deeper what is actually the anomaly. Basically, before going to Asterra, we wanted something pre-trained Dino as well, but we wanted also our ground truth that we knew that model is actually showing finding some kind of anomalies, and we are sure in that. So that's why we use on variational authenticator the bench of loaded images, preloaded images like from our open source.
So there's no labeling in the open source.
There is no labeling. That's why we come up with artificial intelligence.
Okay.
That's what I told you before. Like the label could be easily. It's about your approach, right? You're training the small model and say, hey, you know the agricultural fields. Boom, you are giving her bare land, and she pointed an anomaly. True, right? For the model, for the data it was trained on. So it's very like we need to know what is our anomaly. Basically, getting back to your time series of the area of interest. Through the time series, we also understood, and Google Earth Engine helped us a lot, that there is some kind of deviation of the lakes, like, sometimes it's more, sometimes it's less. Basically, which model, if she doesn't know exactly where to look at, and this is the range of my like spreaded function, she can say, here, this is the leak, this is leak, because like there is a bigger or smaller like distribution of pixels. But basically, because we use the area of interest, in some point we can predict like, no, that can be also the deviation of the function.
So you didn't use the sequence.
We did use in variational authenticator. We did use the area of interest, right, and sequence of the data from 5 years. I think we did it. Like it's not always perfect, like and you're killing basically the machine, but in Kaggle you have a quote, so you're getting it every week. So problem was I was killing it every 2 days.
So you're the group that needed the
Yes, that was good. So it was so we tried. Yeah, we tried, and again, it's open source. Everyone can go and actually supply the data they need, and based on this data, we can get somewhere with this.
Okay. And there was at the end, towards the end, you had like the measurements and results of the precision of the F1. You mentioned in the beginning that the thing that was most important for the company was the reform.
Yeah.
But I think it wasn't.
Yeah.
So why did you? Oh, there it is. Missed that.
Yeah.
Yeah. Okay, there it is. I wanted to say thank you for the enthusiasm. It was a lot of energy. Thank you.
You said you checked 4 models, right?
Yeah, we used 4 models in the fall.
And the first was the statistical one? Right?
Yeah.
And then you included in the ensemble?
A statistical one is actually like, the fast score. Again, because we're open source, we can give the manual drive to the end user. You can decide if the 35 is the extreme score for you, cut it. Just don't proceed it further. But if the situation like we saw 1720, when 20 goes to the normal image and 17 stays on the like anomalous image, maybe it's what I see. So you're basically playing with threshold.
In the ensemble, or you put them, you're not applying everyone parallel?
For the deep learning models, yes, but you can't treat like the statistical algorithm the same way you're treating the deep learning model.
Yeah, but why even include the statistical one? It gives less result.
If we can go to the very first slide of like the very first slide. Oh, no, that one. That one. Yeah, because of these cases. Like mostly. Like that would be a very high score. This one will be missed. So you basically what deep learning machine, it's resources. Resources is expensive. So if you can hard score like with this image.
Okay, so you won't apply all the models at once. You try the cheaper one.
Exactly, the cheap.
Okay, so
Yeah, but again, what I'm trying to say, it's you to decide. Maybe you're Google, you don't care. Like, but in this case, you don't care about anything. Apply 6 right away.
If you Google, you don't care at all.
Yeah, you just go to diamond.
Thank you.
Thank you. Thank you, guys.